in the back? Yeah? All right, thank you. So I'm going to talk about stellar disk kinematics and rare stars in M31 and M33. The M33 work is in progress, and I don't have as much of it as I had anticipated, so I'll focus on M31 here, but I'll say a few words, even though I don't have any results to show for M33. This work on M31 that I'm going to talk about was done with Sandy's wonderful spectrograph DEIMOS on the Keck-2 telescope, and I'll also say a little bit about the HST photometry that's gone into this science. So it's spectra from Keck and 6-band photometry from Hubble that we've used to study the stellar disks of M31 and M33. This is part of the SPLASH survey, the spectroscopy is, but the photometry is part of the FAT survey led by Julian Del Canton. And the T in FAT used to be triangulum. It was panchromatic Hubble, Andromeda, and triangulum survey. The TAC cut out triangulum, just gave us Andromeda, so T became treasury for a little while, but then we went back to the TAC and they gave us M31, so FAT has become Andromeda and triangulum once again. Okay, so I'm going to look at these two galaxies through two different lenses, and one of the lenses is using stellar kinematics to study the evolutionary history of the disks of those two galaxies, and the other is taking advantage of the fact that these are large galaxies that represent a lot of stars at a common distance from us, and can we use them as laboratories to study stellar evolution? So I'll say a little bit about each of these two topics. So I've shown this next thing here before, but this movie never gets old for me, so I'm going to show this again. This is the arc of the Milky Way with, that little blip is Andromeda. We're going to zoom in using this HST mosaic, a large mosaic of about 3,000 images. We're going to zoom in until you can see individual stars and the variety of individual stars in a small piece of Andromeda's disk. You can see dust lanes, and you can see star clusters in this image. You can really see patches of dust where some of the stars in those patches are red. Those are the ones that are behind the dust, and there are stars that are in front of the dust. There's been some beautiful work done on the dust by Julian, measuring the amount of dust, but also the geometry of the stellar disk. Because Andromeda's disk is close to edge-on, you can use the fraction of foreground stars, stars in the foreground of the dust disk, to say something about the thickness of M31 stellar disk. And it's becoming clear that M31 stellar disk is like the Milky Way thick disk rather than its thin disk. Okay, so this is the HST component of it, and here is a representation of the Keck component of this survey. These colored dots, the white squares, by the way, represent a subset of the HST survey. They were done in these bricks where 6-band photometry, 2 in the ultraviolet, 2 in the optical, 2 in the near infrared. But the colored dots represent stars for which we got spectra with Keck and DEIMOS. And we filled in some of these gaps later. Once the HST photometry came in, we filled in some more of the gaps that you see there. It's not full coverage of M31's disk. It's coverage of about a third of the bright disk. Okay, and so we selected some stars using CFHT photometry, but most of the things were selected using FAT. Taking a brief look at M31 stellar disk kinematics as a function of stellar age, we looked at 3 aspects of M31. And the first piece of this, Stefan and I worked together on, which is looking at the surface brightness distribution, surface brightness profiles of the bulge disk and halo components of Andromeda's, of Andromeda, the 3 components that one normally associates with a large disk galaxy. The maroon line there, is this a laser pointer? This one, okay. So this maroon line represents the disk, represents the bulge. The, let's see, the green line is the halo, red is the disk. And the thing that is very convincing, if you look at a surface brightness map of Andromeda, it's very clear that the bulge doesn't go out very far. Soon, as you're going out along the minor axis, especially, even if you go out along the minor axis, the disk dominates beyond a certain radius. So this all fits together nicely. And if you look at, however, if you look at the kinematics, out at a radius where the disk should dominate, there's a significant dynamically hot component, again represented by that this purple line here, significantly offset from the main disk population in terms of not having as large a rotation velocity and having a large velocity dispersion. And then the third piece of information one can throw into this is to look at use HST to look at the luminosity function of stars as a function of position. And we realized there was this tension. And I remember Stefan and Larry Widrow and I worked on this for a long time. There's this tension where it looked like if you went out a certain distance on the minor axis, the surface brightness profile screamed out disk, because you're dominated by disk. The luminosity function suggested that it was disk-dominated because the luminosity function didn't have the traditional break at the tip of the red giant branch that you associate with old populations. But the kinematics called out for a dynamically hot population. And one way to resolve the tension is to say some fraction, about 15% of the stars in that part of the disk, if they've been dynamically heated, then you can resolve this tension. The luminosity function, brightness information, and kinematics all fit together. So this was the subject of Claire Dorman's paper. This was the second paper from her PhD thesis here at Santa Cruz. And then she went on to taking the HST photometry and dividing stars into 3 age groups. You take the old red giant stars that have been around for, on average, have a lifetime of about 10 billion years. So the average, if you have a constant star formation rate, the average star in Andromeda has been around for about 5 billion years. Those are shown in the lower left. You have intermediate age AGB stars. These are luminous AGB stars above the tip of the giant branch. They're intermediate mass, a few solar masses, the ages of a few billion years. And then in the upper left, you have young main sequence stars. These are massive stars in the mass range, 5 solar masses and greater. And they're still on the main sequence. They have lifetimes of much less than 1 billion years. And the color coding represents the velocity dispersion, the line of sight velocity dispersion as a function of position. So for every star, you draw a small circle and you measure the velocity dispersion of the neighbors. And it's very clear to see that the dispersion scale on the upper axis tells you that the short-lived stars have a low velocity dispersion, 20 to 30 kilometers per second, but it shoots up to something like 100 kilometers per second by the time you get to the old RGB stars. They show systematic rotation, as I'll show you in a minute. Again, this is how the stars were, in that 2-panel diagram there, that one. This is the overall fat CMD, shown as a Hess diagram, a combination of Hess diagram and dots. The green box is the subset of that CMD where stars are bright enough for us to get spectra. And that green box has been zoomed into on the right panel. So these blue stars are the upper main sequence. And you're wondering, why is the main sequence vertical? It's because we're using B and I band photometry, and these stars are getting so hot that we're on the Rayleigh-Jeans side, so we're not seeing this variation in temperature translate into a variation in color. The stars are hot enough for that. The red stars are old RGB stars, and the AGB stars in that particular version have been divided into luminous and less luminous AGB stars. And here is what their velocity dispersion looks like. There's a histogram for velocity dispersion. We could measure the velocity dispersion around the disk of Andromeda. And the velocity dispersion is really high for these long-lived stars. Another way of looking at this is looking at velocity dispersion as a function of the mean estimated stellar age. And the mean age depends on what you assume for the star formation history of Andromeda's disk, of course. And so those are 2 different assumptions. But compare that to the Milky Way solar neighborhood measurements, and you get something that's significantly elevated in terms of 0 point and significantly steeper. So the rate of dynamical heating appears to have been higher in M31, and the amount of dynamical heating appears to have been higher in M31's disk. This was the work of Claire Dorman. Again, this paper came out in 2015. Claire is making big bucks at Pandora. She doesn't care about Andromeda anymore, but no, she does care about Andromeda still. Okay, so I'm going to transition quickly to another student's work, Amanda Quirk's work. She has a poster up at this conference. And what you're looking at now, again, is stars color-coded by velocity. In the upper panel, individual stars divided into these 4 groups: main sequence, young AGB, older AGB, RGB. And in terms of time, something like less than 100 million years up to several, less than 100 million years to, up to several billion years. And it's a little difficult to see in the colors of individual stars, but if you smooth the map, that is, if you replace each star's velocity by the mean velocity of its neighbors, not velocity dispersion now, but mean velocity of the neighbors, you can see that the range of velocities now, so you're seeing a rotation pattern, you can see a clear trend, that the range of velocities is greatest for the youngest, shortest lived stars. The range of velocities, while significant, is not as high for the longer lived stars. So there's asymmetric drift relative to the H1. The H1 map looks a lot like this. So the youngest, the shortest lived stars have practically 0 asymmetric drift, but the oldest stars, the longest lived stars, have significant asymmetric drift. Okay, how am I doing for time? All right. How much do I? Okay, good. All right. So I'm going to transition a little bit and talk about rare stellar population. All right. Thank you. Thank you. Rare stellar populations in the disks of M31 and M33. So, you know, we use these spectra to measure radial velocities by comparing them to stellar templates, spectral templates. But one of the natural byproducts of that process is finding out what type of star you have there. If you have a wide enough library of spectral types, you pick up unusual stars in Andromeda. And we found about 100 stars that look like this. And to the theorists in the audience, and maybe even to the spectroscopists in this audience, this looks like the data are horrible. They're just so jagged and noisy. But if you look closely, the corrugations are the same in these 3 different spectra. These are dramatic examples of molecular absorption, carbon-rich molecules that have been dredged up to the atmospheres of these, into the atmospheres of these stars. And by looking at where these stars are in a color magnitude diagram, they're consistent with where evolved AGB stars, intermediate mass AGB stars, are supposed to be in the CMD. They're above the tip of the old red giant branch. They're somewhat red, and their spectra are drawn from a mold. They're all alike. These are 3 stars here, and I've identified the pink band on the right there. This, with a little bit of imagination, you can see a W shape in that pink band. That's produced by the molecule cyanogen, CN, and it's at about 8,000 angstroms. And I want you to focus on that W. You know, pretty much every feature here is related to a carbon-rich molecule. Now, we came across stars like these that look relatively normal. You can see in blue, you can see the calcium triplet. I'll point to it. The calcium triplet is right there, 3 absorption lines. This is titanium oxide, these steps over here. But in this same 8,000 angstrom region, there's a little bit of a hint of this same W. It's much weaker, but there's a hint of this. Now, when I was learning stellar evolution on my mother's knee, I was told that stars either have oxygen-rich molecules in their atmospheres or they have carbon-rich molecules in their atmospheres. So here's an example, 3 examples of stars that have maybe carbon comparable to oxygen rather than one dominating over the other. The cool thing about these stars is while they're a little difficult to find visually, you can take a carbon template like this, dilute it, add it to a normal star template, and see what mix best fits the spectrum. So we're using simple techniques like these to identify these. We found about 100 carbon stars, about 200 weak CN stars. they land in different parts of the color magnitude diagram. So let me show you where they land. But before I do that, the carbon stars was the work of Katie Hamron, who got her PhD a year after Claire, 2016. And the weak CN work was actually the work of 3 high school students and a community college student who started this work a few years ago. They did remarkable work, and here you go. Here they are in a color magnitude diagram. The green points are the traditional carbon stars. The blue points are these weak CN stars. And again, they outnumber, the weak CN stars outnumber carbon stars by about a factor of 2 to 1. These are different CMDs. You've got sort of J minus H versus H at the top. You've got a more traditional I versus B minus I at the bottom. And you can see a separation between the carbon stars and the weak CN stars. So here's a third CMD now with I minus H on the x-axis. I'm calling them I minus H. It's really F814 minus F. Thank you. And F160 as the magnitude. And what's overlaid on this are part of our isochrones corresponding to masses of 1, 2, 4, 5, 10, and 12. So 1, 2, 4, and 5. It's hard to see the cyan line, 4 and 5, and then 10 and 12. And you might notice that in this case, the weak CN stars are marked in orange. Sorry to change the color on you, but they're marked in orange here. The carbon stars are in green. But you'll notice this kink in the isochrones of these massive stars. This is where stars are evolving off the main sequence. Massive stars in the range 4 to 10 solar masses are evolving off the main sequence. They have helium in their core. So this is sort of the core helium sequence in M31, which would otherwise be difficult to pick out at a CMD. We seem to be picking them up through spectroscopy. So the Padova group is involved in the FAT survey. They're quite excited about this. They are barely at the point where their models can model carbon stars. So we're throwing them a challenge, a weak CN star challenge, before they've mastered carbon stars. But they're quite excited about this. And this is yet another version of the CMD where they seem to be consistent, at least in CMD space, with more massive stars, 4 to 10 solar masses, these weak CN stars. So again, evolved stars in the mass range, 4 to 10 solar masses. I'll give you a little bit more insight with this CMD. Remember how I said the hot stars tend to collapse if you're not using the right pair of band passes to measure color. So here we're using F336 minus F475W, like a U minus B. And what happens is the main sequence and blue loop, the blue loop is the part associated with this kink in the isochrones. This blue loop and main sequence separate out very nicely when you use the ultraviolet filter. And it's clear that there are some weak CN stars associated with this. This is sort of the blue core helium sequence, and there's a red core helium sequence, which is hard to see in Andromeda because it's got such a big metallicity spread that the red giant branch spreads out and sort of overlaps. Okay, so again, the weak CN stars appear to be in this mass range. And then finally, we've looked at kinematics. Oh, before we do that, we've looked at the details of the spectrum. So you can take a star. If you have a spectrum of a star and you normalized it, you can subtract a constant from it and renormalize it. And if you do that, you've effectively strengthened all the absorption features. So if we do that, if we strengthen the features by a factor of 3 in the weak CN stars and compare them to 3 different subgroups of carbon stars, you can see a lot of commonality in the fine-scale features. You can see this broad W that we saw earlier, but you can see a lot of fine-scale features that we are yet to identify. This is what we're throwing at the Padova group. They're going to model this for us, hopefully sometime in the next decade. But ordinary stars, oxygen-rich stars, look nothing like that. There are some features in common. Those are what's in blue. But everything in pink is things that are not seen in oxygen-rich stars but are seen in carbon stars. All right, so we looked at the kinematics, and it looks like even from the kinematics, the same sort of idea. We look at the velocity dispersion of the population. Weak CN stars have a lower velocity dispersion than the carbon stars, suggesting that they are more massive. They're consistent with being more massive than the carbon stars. So to summarize, our stellar velocity dispersion and asymmetric measurements of stars of a range of lifetimes suggests a steady increase, a steady dynamical heating of the disk in the lifetime range for stars from less than 1 billion years to about 10 billion years. And the discovery of weak CN stars is something I reported here that appears to be associated with evolved stars in the mass range, 4 to 10 solar masses. That's where I'll stop. Thank you.
Questions for Raja? Back, perhaps? For the back, we'll go to David.
Catherine.
Picking up this population in other galaxies, do you have ways of doing that without?
We're going to do this in M33. And there the velocity dispersion, the line of sight velocity dispersion is closer to the Z component. In M31, because it's close to edge-on, we're really looking at the tangential and radial components. So it'll be a little bit of apples and oranges, but we're planning to do this. We've got about 2,000 spectra, same sort of thing, division of stars by age in M33. We're in the process of churning through those data. We've collected the spectra already, but yeah, we're very excited to see what that holds for us. Its evolutionary history is almost certainly different from Andromeda. It's much harder to do in the Milky Way because we're stuck inside it, but doing it in these two galaxies is a good way forward. We're looking at all of the same things: asymmetric drift, velocity dispersion as a function of stellar age, and these rare populations.
Is there any way that you can tell whether any of the stars are actually binary in some way? Is there signature that kind of wiggle in the velocities, or there's some signature that
Yeah, so the question from David is a binarity in these stars. Most of the stars that we have spectra for are evolved stars, so they're quite large, and any kind of binarity would involve velocities that are of the order of a few kilometers per second. So it will be, they're not important for affecting the velocity dispersions we measure, but they're actually also hard for us to detect. It's different when you're talking about ultra-faint dwarfs, where I know Josh Simon, Marla Jiha, Evan Kirby have looked at, they have found evidence of binarity. There we're talking about turn-off stars, so we're talking about lower velocity dispersion, so binarity can play havoc on what you infer about the velocity dispersion. So it's very painstaking work, but having to go back and remeasure velocities that are already very hard to measure. So they have found binaries there.
these stars expect to have big dark splotches all over it, or
These,
on the surface?
that's well outside my my wheelhouse. So David's asking about star spots. Yeah, star spots. We are measuring variability in these stars. We are, but that's mostly, and it's aperiodic. These stars, many of these very luminous stars, have variations on 100 to 1,000 day timescales. And it turns out the way the FAT survey was done, there's actually a time domain component within it. So we're starting to explore that. All right.
We got a bit of time.
Frank. Oh, Charlie. Okay.
In the Milky Way, there's classic oxygen-rich stars, carbon stars, and then these S stars.
Yeah, that's what I think these things are.
Carbon to oxygen basically equal to the chemistry
Right.
intermediate between the two.
That's right.
Is that what you?
That's what I think they are, but they're actually a little harder to track down in the Milky Way because we don't know distances, whereas here we have a bunch of stars at a common distance. I think that's exactly what they are, but there's some cool things about this, right? So I said they're associated with a more massive population, and the evidence points to that, yet they're twice as numerous as the carbon stars. So this says to me that the third dredge-up that produces carbon stars is a smaller fraction of intermediate mass stars' lifetimes, and these are of the 4 to 10 solar mass stars' lifetime. So just the counts are starting to tell us something.
There's also a metallicity dimension to this.
There's almost.
More efficient, you can make carbon stars easier at low metallicity.
Right, that's right. Yeah, there could be. And so I think what we are seeing in M33 is these stars are wild in M33. By number, they greatly outnumber carbon stars in M33. And that is indeed a lower metallicity galaxy.
Frank, you don't have to be quick. You're good? We're good? Okay, thank you. Thank you very much.
All right,
for
all
your
right.
presentation. Two quick messages. I'd like Catherine, Charlie,